July 25th, 1943. Telefunken Research Laboratory, Berlin. The metal fragments scattered across Oberst Wolfgang Martini's desk glittered under the harsh fluorescent lights like confetti from some perverse celebration. Aluminum strips, each precisely cut to 27 centimeters in length, half a centimeter wide, weighing almost nothing. He lifted one between thumb and forefinger, turning it slowly, watching light play across its surface. "This cannot be deliberate," he murmured to the assembled engineers. No air force would waste payload capacity on scrap metal, but the mathematical evidence told a different story. The previous night, July 24th, 1943, German radar screens from the Frisian Islands to the Danish coast had simultaneously registered what appeared to be 11,000 aircraft approaching Hamburg. 11,000. The entire RAF Bomber Command possessed fewer than 1,500 heavy bombers, every Freya and Würzburg radar installation within 200 kilometers had shown the same impossible reading. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Screens white with returns, operators frantically calling fighter control. Night fighter units scrambling to intercept a formation that should have blackened the sky with its physical presence. Instead, 246 RAF bombers, carrying nothing more revolutionary than thousands of bundles of aluminum strips, had rendered the entire German air defense network blind. The strips had been collected that morning from rooftops and streets across Hamburg, gathered by Hitler Youth members who thought they were cleaning up debris from the previous night's attack. When the first samples reached Luftwaffe intelligence, confusion gave way to disbelief, then to the slow, crushing weight of realization. The British had found the frequency. They had measured the wavelength of every German radar system. They had calculated the precise dimensions required to create false returns. They had manufactured these countermeasures in sufficient quantity to saturate an entire defensive network. And they had deployed them with such coordination and effect that German fighter control had been reduced to panicked impotence, vectoring night fighters toward ghost formations, while real bombers streamed through undefended corridors toward their targets. Martini, as Chief of Luftwaffe Signals Intelligence and the officer responsible for all German radar development, understood the implications immediately. This was not tactical surprise. This was systematic defeat. The British had studied German defensive systems with scientific precision, identified their vulnerabilities, and exploited them with an elegance that bordered on contempt. Every assumption about radar superiority, every calculation about defensive effectiveness, every confident prediction about Hamburg's impregnability, all rendered obsolete by strips of aluminum that cost almost nothing to produce and could be scattered by the thousands from aircraft bomb bays. The psychological transformation had begun, not with battlefield defeat, but with the recognition that the enemy understood German technology better than the Germans understood British intentions. Through the laboratory windows, Martini could see smoke still rising from Hamburg's ruins. The fires had burned for 3 days. Casualty estimates remained uncertain, but preliminary reports suggested thousands dead, perhaps tens of thousands. The attack had been code-named Operation Gomorrah by the British, a biblical reference to divine destruction of a sinful city. The hubris was unmistakable, but so was the accuracy. Hamburg, Germany's second-largest city and most important port, had been transformed into a vision of apocalypse by an enemy that had solved the radar problem with such simple, devastating effectiveness that German defensive doctrine lay in ruins alongside the shattered buildings. What neither Martini nor his colleagues fully grasped yet was that this was only the beginning. The aluminum strips, which the British called window and the Americans would call chaff, represented not merely a tactical countermeasure, but a fundamental shift in the electromagnetic warfare that had been waged invisibly alongside the conventional conflict. The air war over Germany, which had claimed thousands of British air crews and killed tens of thousands of German civilians, had been fought within strict parameters defined by radar detection and fighter interception. Those parameters had just been shattered. The fragments on Martini's desk were evidence of a breach in the defensive wall that had protected German cities from unrestricted bombing. More critically, they suggested that British scientists possessed detailed knowledge of German radar systems, their operating frequencies, their detection methods, their vulnerabilities. This was not information that could be derived from theoretical physics alone. This required measurement, testing, analysis. The British had been studying German radar emissions for years, cataloguing frequencies, timing pulses, power levels. They had built a comprehensive understanding of German defensive systems, while German intelligence remained largely ignorant of British capabilities. The asymmetry was profound and terrifying. The story had begun much earlier, in the strange world of electromagnetic warfare that existed parallel to the conventional conflict. As early as 1940, British scientists had understood that German radar operated primarily in the meter wavelength range, specifically between 2 and 4 meters for early warning systems like Freya and around 50 to 60 centimeters for gun-laying and fighter direction radars like Würzburg. This knowledge came from multiple sources. WWII listening stations intercepted German radar transmissions, measuring their frequencies and characteristics. Reconnaissance flights deliberately provoked German radar systems, mapping their coverage and identifying their locations. Captured equipment from shot-down aircraft and overrun positions provided physical examples for examination. By 1941, the British possessed detailed technical specifications for most German radar types. The vulnerability was obvious. Radar works by transmitting electromagnetic pulses and measuring the time required for those pulses to reflect from targets and return to the receiver. The size and shape of the target determine the strength of the return signal. An aircraft, with its large metal surface area, produces a strong return, but any conductive material of appropriate size can produce a similar return. If that material is cut to a length equal to half the wavelength of the radar frequency, it becomes a perfect resonator, reflecting the radar energy with maximum efficiency. For Freya radar operating at a wavelength of 2.4 meters, the optimal chaff length would be 1.2 meters. For Würzburg at 53 centimeters, the optimal length was approximately 27 centimeters. The mathematics were straightforward. The implementation was equally simple. Aluminum foil, readily available and cheap to produce, could be cut into strips and bundled together. When released from aircraft, these bundles would separate, creating clouds of individual reflectors. Each strip would produce a radar return similar to that of an aircraft. Thousands of strips would produce thousands of apparent aircraft, overwhelming radar operators and rendering detection of real bombers impossible. The concept was understood by both British and German scientists from the earliest days of radar development. Both sides recognized the potential for such countermeasures. Both sides chose not to deploy them initially, not because of technical limitations, but because of strategic fear. The worry was simple and symmetrical. If Britain used chaff against German radar, Germany would immediately copy the technique and use it against British radar. If Germany used chaff first, Britain would retaliate. The result would be mutual blindness, with both sides' radar networks rendered useless. This created a strange equilibrium, a tacit agreement maintained through mutual fear rather than any formal treaty. Neither side wanted to be the first to break this seal, knowing that once broken, it could not be restored. British scientists had actually developed operational chaff as early as 1942. The code name Window reflected its ability to open a transparent path through German defences. Extensive testing had confirmed its effectiveness. Bundles of metallized paper strips, each cut to precisely 27 centimeters to match Würzburg radar frequency, had been manufactured in quantity. Production was ready. Tactical doctrine for deployment had been written. Bomber crews had been trained. Everything was prepared except the political will to use it. The decision remained frozen throughout 1942 and into 1943. Air Chief Marshal Arthur Harris, commander of RAF Bomber Command, argued repeatedly for Window's deployment. His bombers were suffering unsustainable losses over Germany, particularly during deep penetration raids against heavily defended cities. German night fighters, directed by radar-controlled ground stations, were achieving kill rates that threatened the entire strategic bombing campaign. In some raids, bomber losses exceeded 10%, well above the 5% threshold considered sustainable for long-term operations. Window, Harris argued, could reduce those losses dramatically. If German radar could be blinded, night fighters would be reduced to random searching in vast empty skies. The odds would shift decisively in favour of the bombers. But the counter-argument was equally compelling. Britain's own air defences relied heavily on radar. The chain-home network that had helped win the Battle of Britain in 1940 still formed the backbone of early warning systems. Gun-laying radars directed anti-aircraft fire. Ground-controlled interception radar guided night fighters against German intruders. If Germany retaliated by using chaff against British radar, these defensive systems would become useless. The German Luftwaffe, though weakened by years of attrition on the Eastern Front, still possessed enough bombers to inflict significant damage on British cities if given free access. The memory of the Blitz remained fresh. The idea of inviting its renewal by blinding British defences seemed recklessly dangerous. Churchill himself agonised over the decision. The minutes from War Cabinet meetings throughout 1942 reveal the tension between offensive advantage and defensive vulnerability. The Prime Minister wanted to strike Germany with maximum force, but he could not ignore the possibility that such strikes might leave Britain defenceless against retaliation. The deadlock continued through the winter of 1942–43. Bomber Command losses mounted. Harris's frustration grew. The strategic bombing campaign, which was supposed to break German industrial capacity and civilian morale, was instead grinding down British aircrews at rates that threatened to make the campaign itself unsustainable. Something had to change. The breakthrough came from an unexpected direction. Intelligence assessments in early 1943 suggested that German bomber forces had been so depleted by losses on the Eastern Front that they no longer possessed the capacity for sustained strategic bombing of Britain. The Luftwaffe's focus had shifted almost entirely to tactical support of ground forces fighting in Russia and defensive operations against Allied air attacks. German bomber production had been subordinated to fighter production. Crew training emphasized defensive tactics rather than offensive bombing. Most critically, German defensive radar doctrine had been optimized for protecting German cities against Allied attack, not for protecting German bombers during attacks on Britain. The asymmetry was clear. Britain had much more to gain from blinding German radar than Germany had to gain from blinding British radar. The risk of retaliation still existed, but the magnitude of potential German response had diminished significantly. Combined with growing confidence in British night fighter effectiveness even without radar, the balance shifted. On July 15, 1943, Churchill authorised the use of window. The operational order went to Bomber Command on July 22nd. The first mission using the new countermeasure would be the opening attack of Operation Gomorrah, the sustained bombing campaign against Hamburg scheduled to begin July 24th. The choice of Hamburg was deliberate. Germany's second city, vital port, major industrial centre, heavily defended by radar-controlled flak batteries and night fighter units. If window worked against Hamburg's defences, it would work anywhere. The city's radar network was typical of German air defence systems. Multiple Freya early warning radars detected approaching formations at long range. Information passed to Würzburg gun-laying radars that directed flak batteries. Separate Würzburg sets tracked both bombers and night fighters, allowing ground controllers to vector fighters onto bomber streams through a system called Himmelbett, or bedpost. The entire network operated with practiced efficiency, developed through years of defending against RAF raids. Hamburg's defenders shot down dozens of British bombers every month. The city was a graveyard for aircrew, a testament to German defensive mastery. The 791 aircraft that assembled over England on the evening of July 24, 1943, included 746 bombers, carrying approximately 2,200 tons of bombs and 92 million strips of aluminum. The latter weighed just over 40 tons total, insignificant compared to explosive payload, but infinitely more valuable in effect. Each bomber carried bundles of window, packages of 2,000 strips bound with rubber bands. These bundles were stacked near the aircraft flare chute, ready for deployment. Crews had been briefed on the new weapon, though many were skeptical. Paper and aluminum against German radar seemed like magical thinking, too simple to work, too strange to be real. But orders were orders. At specific intervals after crossing the German coast, crew members would feed bundles down the flare chute, one bundle every minute, maintaining a continuous stream of chaff. The bomber stream crossed the North Sea in gathering darkness. German radar operators along the coast picked up the formation at approximately 10:15 post-meridium, roughly 60 miles offshore. Standard procedure initiated. Fighter control alerted. Night fighter units scrambled. Flak batteries prepared. The defenders had handled hundreds of raids before. This would be no different. Then, at approximately 10:30 post-meridium, the radar screens went white. The phenomenon started at coastal stations and spread inland as the bomber stream advanced. Freya operators suddenly saw not a single large formation but dozens, then hundreds, then thousands of distinct returns. The screens filled with targets moving at bomber speed, approaching from the north, impossible to distinguish real aircraft from false returns. Radio discipline collapsed as operators reported the impossible numbers: 11,000 contacts, 12,000. Estimates varied wildly because counting became meaningless when the entire screen showed nothing but bright green returns, packed so densely they merged into a solid glow. Fighter control attempted to vector night fighters toward the densest concentrations, assuming real bombers must be somewhere in that electronic fog. But the pilots found empty sky. They flew through clouds of falling aluminum that their aircraft propellers chopped into glittering fragments, but no bombers. The British formation had dispersed into individual aircraft streams, taking advantage of the radar confusion to spread across a wide front. Some night fighters scored kills through pure chance, visual contact in moonlight or illumination from searchlights, but the systematic radar-controlled interception that normally characterized German night defense had broken down completely. Flak batteries faced similar chaos. Würzburg gun-laying radars that normally tracked individual bombers with precision accuracy now showed dozens of targets simultaneously. Gun crews fired at the most promising returns, but most shells exploded harmlessly among clouds of chaff. A few aircraft were hit by barrage fire, shells sent up in volume toward areas where bombers were likely to be, but the directed fire that made German flak so deadly had been neutralized. The bombers pressed through to Hamburg, almost unmolested. 746 aircraft dropped their loads across the city in less than an hour. High-explosive bombs shattered buildings and ruptured gas lines. Incendiary bombs ignited fires in wooden structures throughout the older districts. The concentration of impacts, combined with dry summer conditions and dense urban construction, created ideal conditions for what would follow. But that first attack, devastating as it was only the opening blow. The British returned 3 nights later, July 27th to 28th, with 722 bombers carrying more high explosives, more incendiaries, and more window. By then, Hamburg was already burning from the first raid and from American daylight bombing on July 25th and 26th. The second RAF attack hit a city where firefighting resources were exhausted, water mains were damaged, and thousands of small fires still smouldered in rubble. The combination of factors created something unprecedented in the history of warfare. The firestorm began in the early morning hours of July 28th. Individual fires merged into a single conflagration that generated its own weather system. Superheated air rose rapidly, creating a powerful updraft that sucked in cooler air from surrounding areas at ground level. These inrushing winds reached speeds of 150 kilometers per hour, hurricane-force winds feeding a fire that consumed everything combustible. Temperatures in the fire zone reached 800 degrees Celsius, hot enough to melt glass, ignite asphalt, and cause spontaneous combustion of materials normally considered non-flammable. People caught in the firestorm died from multiple causes simultaneously. Some suffocated as the fire consumed all available oxygen. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Some died from carbon monoxide poisoning. Some were simply incinerated where they stood, reduced to ash and charred bone by temperatures that exceeded crematorium furnaces. Those who sought shelter in basements found that the buildings above them collapsed, sealing them in tombs, or that the heat penetrated underground, baking them alive. The firestorm burned for 3 hours at peak intensity. When it finally exhausted its fuel and died down, approximately 8 square miles of Hamburg had been completely destroyed. Casualty estimates remain uncertain even decades later, but most historians agree that at least 37,000 people died, possibly as many as 45,000. The majority perished in the firestorm of July 28th. Approximately 1 million civilians fled the city in the following days, creating a refugee crisis that strained German civil defense systems across northern Germany. Hamburg's industrial capacity was reduced by approximately 50%. Port operations were severely disrupted for months. The psychological impact on German civilian morale was profound and lasting. But from Martini's perspective in Berlin, studying the aluminum strips collected from Hamburg streets, the human cost, horrific as it was, represented only one dimension of the catastrophe. The technical implications were equally devastating. The British had demonstrated complete understanding of German radar systems. They had developed countermeasures that cost almost nothing to produce but rendered sophisticated radar networks useless. They had deployed these countermeasures with operational skill that suggested extensive planning and preparation, and they had shown willingness to break the tacit agreement that had kept both sides from using chaff, calculating correctly that German retaliation would be minimal. The question facing German scientists and military commanders was stark and immediate. What could be done? Martini convened emergency meetings with Germany's top radar specialists throughout the final days of July 1943. Representatives from Telefunken, Siemens, Gemma, and Lorenz attended, along with Luftwaffe operations officers and anti-aircraft artillery specialists. The discussions revealed a landscape of limited options and painful trade-offs. The fundamental problem was straightforward. Chaff worked because it created radar returns similar to those of real aircraft. Distinguishing real returns from false returns required methods that went beyond simple detection. Several approaches were theoretically possible. First, frequency agility. If radar systems could rapidly change their operating frequency, chaff cut for one wavelength would become ineffective at other wavelengths. However, implementing frequency agility required completely new radar designs. Existing systems had fixed frequencies determined by their cavity magnetrons or other RF generation systems. Modifying them would be equivalent to building entirely new radar networks, a process that would require years and resources Germany did not have. Second, Doppler discrimination. Falling. Chaff descends at a relatively slow rate compared to aircraft flying at 200 miles per hour. A radar system that could measure the Doppler shift of returned signals could theoretically distinguish between fast-moving aircraft and slow-falling chaff. But Doppler radar was still experimental in 1943. German scientists understood the principles, but operational systems did not exist. Development would require extensive research and testing, followed by production and deployment, again a timeline measured in years rather than months. Third, pulse compression and advanced signal processing. More sophisticated analysis of radar returns could potentially identify characteristics that distinguished aircraft from chaff clouds. But this required computing capability far beyond what was available in 1943. The analog systems that processed radar signals in real time could not perform the complex calculations necessary. Digital computers that might handle such processing existed only in the most primitive forms, filling entire rooms and requiring enormous power. Fourth, visual confirmation. If radar could not reliably distinguish targets, human observers would have to do so. Searchlights could illuminate suspected bomber formations, allowing visual identification before night fighters were vectored to intercept. But this meant reverting to tactics from the pre-radar era, tactics that had proven inadequate against the speed and altitude of modern bombers. It also required perfect weather conditions. Clouds or haze rendered searchlights useless. The limitations were obvious. Fifth, accept the degradation and adapt tactics. If radar could no longer provide precision tracking, German defences would shift to area defence. Flak would be fired in barrage patterns rather than aimed at specific targets. Night fighters would patrol likely bomber routes rather than being vectored to specific intercepts. It was a confession of defeat, an acknowledgement that German defences could no longer match British offensive capabilities, but it might be the only realistic option. The meetings produced consensus on several grim conclusions. Germany could not quickly develop countermeasures to window that would restore radar effectiveness. The technical challenges were too great and the industrial capacity too limited. Existing radar networks would remain vulnerable to chaff indefinitely. Tactical adaptations could reduce but not eliminate the effectiveness of British countermeasures. Most critically, British use of window suggested they possessed detailed intelligence on German radar systems, their frequencies, their deployment patterns, their operational doctrine. This implied either extensive signals intelligence gathering or information from human sources within the German military technical establishment. Either possibility suggested that German defensive security had been comprehensively compromised. The psychological impact on German defensive planners was profound. For years, they had believed that German radar technology was superior to Allied capabilities. The Würzburg radar in particular had been considered a triumph of German engineering, precise enough to track individual aircraft and guide night fighters to within visual range. The British had studied this triumph, measured its vulnerabilities, and neutralized it with aluminum strips that cost a few Reichsmarks per thousand. The asymmetry was humiliating. British scientists had apparently spent years analyzing German defensive systems, while German intelligence had failed to predict or detect the development of window. The British had deployed their countermeasure with perfect timing, waiting until German bomber forces were too weak to retaliate effectively, ensuring that the advantage would be overwhelmingly one-sided. They had demonstrated scientific sophistication, operational security, and strategic patience. German defensive doctrine, by contrast, had been static, predictable, vulnerable. Worse still was the realization that this was unlikely to be the only British surprise. If window existed, what other countermeasures had been developed but not yet deployed? What other German systems had been studied and solutions prepared? The confidence that had characterized German military technical planning in the early war years had evaporated, replaced by defensive uncertainty and the assumption that any German capability might be countered by Allied technology. Defensive planners began working under the presumption that the enemy always possessed better information than German intelligence could provide. Martini ordered immediate changes to German radar operations. Operators were instructed to look for specific characteristics that might indicate real bombers rather than chaff. Aircraft returns typically showed consistent movement in a single direction. Chaff clouds tended to disperse and drift with wind, creating returns that spread and faded over time. These were subtle distinctions, difficult to observe in real time during the confusion of a raid, but they represented the only immediate option for improving discrimination. Searchlight batteries received increased priority. If radar could not reliably identify targets, visual confirmation became essential. Additional searchlight units were deployed around major cities, creating illuminated zones where night fighters might spot bombers visually. The tactic had limited success. British bombers began using various techniques to avoid illumination, including altitude changes and evasive maneuvers. More searchlights meant more power requirements and more personnel, both resources that Germany was finding increasingly scarce. Flak tactics shifted toward barrage fire. Rather than tracking individual targets, Gun crews were ordered to create walls of exploding shells at specific altitudes along likely bomber approach routes. This required enormous ammunition, expenditure, and achieved lower hit rates per shell fired, but it was the only way to maintain some level of threat against attacking formations when precision tracking was impossible. The ammunition costs were unsustainable long-term, but there were no better alternatives. Night fighter tactics evolved to emphasize freelance hunting rather than ground-controlled interception. Experienced pilots were given greater autonomy to patrol independently, using airborne radar when available or visual searching when not, seeking targets opportunistically rather than waiting for ground control to vector them to specific intercepts. This placed greater burden on pilot skill and initiative, and it reduced coordination, but it was less vulnerable to the chaff that blinded ground radar. The changes helped, marginally. Bomber losses over Germany did not drop to zero after Window's introduction, but they declined significantly. In the 6 months before Window, RAF Bomber Command suffered average loss, rates around 4.5% per raid over Germany. In the 6 months after Window, average loss rates dropped to around 3%. That 2% difference represented hundreds of aircrews who survived missions they would previously have died on. It represented thousands of additional tons of bombs delivered to German targets. Most critically, it represented a shift in the sustainable balance of the air war. At 3% losses, Bomber Command could maintain and expand operations. At pre-Window loss rates, the offensive had been approaching unsustainability. Harris had been proven right. The captured documents and interrogation reports from German personnel after the war reveal the depth of German frustration with Window. Luftwaffe fighter pilots described the impossible situation of being directed by ground control toward targets that didn't exist while real bombers streamed past undetected. Radar operators documented their helplessness as screens filled with false returns they could not distinguish from real threats. Flak battery commanders reported ammunition expenditure rates that quintupled after Window's introduction, while kill rates dropped by half. Technical specialists catalogued failed attempts to develop effective countermeasures, each promising approach foundering on practical limitations or resource constraints. The testimony is consistent. Window represented a turning point in the air war over Germany, the moment when defensive superiority shifted irreversibly to the Allied offensive. The German response to Window also demonstrated the limitations of rushed technical development under wartime pressure. Several radar modifications were attempted in late 1943 and early 1944. The Würzburg Rieser, an enlarged version of the standard Würzburg with a 7.5-meter diameter dish compared to the original 3 meters, offered somewhat better discrimination against chaff through improved resolution, but it was expensive to produce and did not fundamentally solve the problem. Freya modifications attempted to incorporate better signal processing, but without advanced electronics, the improvements were marginal. Doppler radar research progressed slowly, hampered by competing priorities and lack of resources. By the time prototype systems were ready for testing in late 1944, the air war had evolved further, with Allied bombers operating in massive daylight formations protected by long-range fighters, rendering the entire premise of radar-directed night fighter interception less relevant. The most successful German adaptation was tactical, rather than technical. Wild sow, or wild boar tactics, developed by Major Hajo Hermann, sent single-engine day fighters up into bomber streams at night, relying on visual identification of bombers silhouetted against fires below or illuminated by searchlights. The tactic achieved some success, particularly during the Battle of Berlin in winter 1943–44, but it was limited by weather, by the need for extensive ground lighting, and by the vulnerability of single-engine fighters operating at night. It was a desperate measure that acknowledged the failure of radar-based defenses. Jachme Sau, or tame boar tactics, paired night fighters with running commentary from ground controllers who provided general information about bomber stream location and altitude, leaving the final interception to the pilot's initiative and airborne radar. This worked better than pure ground-controlled interception in the Window environment, but it required highly skilled pilots and sophisticated airborne radar sets, both of which were in limited supply. The SN2 airborne radar, introduced in 1943, operated at a lower frequency than earlier models, making it less vulnerable to window cut for Würzburg frequencies. However, the British quickly adapted, producing window in multiple lengths to cover various radar frequencies, including SN2. The electromagnetic arms race continued throughout 1944, with each German adaptation met by British counter-adaptation. The fundamental advantage remained with the offensive. The British could study German radar emissions from safety, measure their frequencies, and develop appropriate countermeasures with deliberate care. The Germans were forced to react to British innovations, always defensive, always one step behind, always constrained by limited resources and competing priorities. By mid-1944, German air defences had been degraded to the point where Allied bomber forces operated over Germany in daylight with acceptable losses. The introduction of long-range escort fighters like the P-51 Mustang provided additional protection, but Window's disruption of radar defences was equally important. German fighters struggled to assemble for coordinated attacks when ground controllers could not reliably vector them toward bomber formations. Flak batteries fired enormous barrages, but achieved limited results without precision tracking. The air superiority that would prove essential for the Normandy invasion and subsequent campaigns was built partly on Window's success in neutralizing German radar defenses. The statistical evidence is unambiguous. In the month before Window's introduction, July 1943, RAF Bomber Command flew 5,729 sorties and lost 292 aircraft, a loss rate of 5.1%. In August 1943, the first full month after Window deployment, Bomber Command flew 6,181 sorties and lost 162 aircraft, a loss rate of 2.6%. The reduction was immediate and dramatic. Hamburg suffered again from major raids on July 29th to 30th and August 2 to 3, with both attacks using Window extensively. The defences remained largely ineffective. Total Allied aircraft losses during Operation Gomorrah were 87 bombers from all causes, less than 3% of sorties flown, remarkably low for raids of such intensity against a heavily defended city. German casualty estimates for the entire operation exceeded 40,000 dead. The disparity between attacking and defending losses had shifted decisively. Other German cities followed Hamburg into the flames. Berlin was attacked repeatedly through winter 1943-44, with Window rendering its extensive radar defences largely ineffective. Stuttgart, Mannheim, Leipzig, Frankfurt, Nuremberg all suffered raids where German night fighters struggled to intercept, and flak batteries fired blindly into skies full of chaff. The cumulative effect was both physical and psychological. Cities burned, industrial production declined, civilian morale eroded. But equally important was the German military's growing awareness that Allied technological capabilities exceeded their own, that the qualitative advantages Germany had possessed early in the war had been not just matched, but surpassed. The confidence that had characterized German military culture in 1939 and 1940 had been replaced by defensive pessimism and the assumption that the enemy possessed capabilities beyond German understanding or counteraction. The interrogation reports from captured German radar operators and technical personnel reveal this psychological transformation. They describe their sense of helplessness as British jammers grew more sophisticated, as Window became more prevalent, as Allied electronic warfare expanded beyond simple chaff to include active radar jamming, spoofing, and deception. They document the frustration of operating equipment they knew was obsolete, following procedures they understood were ineffective, participating in a defensive system that had been comprehensively defeated by enemy technology. The testimony is remarkably consistent across different personnel and different locations. They all understood they were fighting a losing battle against an enemy that possessed superior knowledge and superior tools. Martini himself would survive the war and be interrogated extensively by Allied technical intelligence teams. His post-war testimony, preserved in declassified reports, provides valuable insight into German understanding of Windows' impact. "We knew from the first night that this changed everything," he told interrogators in 1945. The aluminum strips themselves were simple, almost crude, but their deployment showed sophisticated understanding of our radar systems. The British had measured our frequencies, calculated the optimal dimensions, manufactured millions of units, and trained crews in their use. This required years of preparation. It required extensive signals intelligence gathering. It required scientific and industrial capabilities we had underestimated. Martini explained that German technical intelligence had known theoretically about chaff since the late 1930s. German scientists had conducted their own experiments with similar concepts, but German leadership had chosen not to deploy such countermeasures, partly from fear of retaliation, partly from confidence that German defences were superior without needing to blind enemy radar. That confidence proved mistaken. The British had been more patient, more thorough, and more ruthless in their application of scientific advantage. He acknowledged that German attempts to counter Window had been largely unsuccessful. The fundamental challenge, he explained, was that chaff exploited the basic physics of how radar worked. Any system that detected, reflected electromagnetic energy would be vulnerable to false returns from appropriately sized reflectors. Solving this required either changing how radar worked entirely, moving to different physical principles, or accepting degraded performance and adapting tactically. Germany had insufficient time and resources for the former, and the latter meant conceding defensive effectiveness. When asked if Germany had developed its own chaff for use against Allied radar, Martini confirmed that such materials had been produced and tested. The German name was Düppel, after a town near where testing occurred. However, large-scale operational use had been delayed until late 1943, months after British deployment of Window. The delay reflected continued fear of further degrading German home defences and uncertainty about whether German bomber forces could effectively exploit Allied radar blindness given their reduced numbers and capabilities. By the time Düppel saw extensive use, German bomber forces were too weak and Allied defences too strong for it to have strategic impact. The asymmetry that had defined Window's success worked in reverse. Germany had more to lose from mutual radar blindness than the Allies, who were winning the war through other means. The post-war technical exploitation of German radar systems by Allied teams confirmed many suspicions about German knowledge of Window. Documents recovered from Luftwaffe archives showed that German intelligence had detected British experiments with radar countermeasures as early as 1942. Reports from agents and signals intelligence had provided warnings that the British were developing chaff and might deploy it operationally. But these warnings had been dismissed by senior Luftwaffe leadership, who could not believe the British would be foolish enough to blind their own defences by introducing chaff into operational use. The failure was one of imagination rather than intelligence. German commanders could not conceive that the British would accept the risk of their own radar being countered in order to gain offensive advantage. They projected their own defensive conservatism onto the enemy and were surprised when the British proved more willing to gamble. The technical analysis of captured Window samples revealed remarkable attention to detail in British manufacturing. The aluminum strips were cut with precision tolerances, ensuring that each piece resonated at the correct frequency. The metallized paper backing provided just enough structural integrity to maintain shape during descent without adding significant weight. The packaging allowed easy handling and rapid deployment from aircraft. Everything about Window's design reflected thorough engineering and extensive testing. It was a mature system, deployed with confidence, not an experimental technology rushed into service. This suggested the British had been preparing Window for much longer than German intelligence had suspected. Later research would confirm this timeline. The British had conducted chaff experiments as early as 1941. The decision to deploy had been made and then delayed multiple times as various. Authorities weighed risks against benefits. The final authorization in July 1943 came after careful assessment that German retaliation capacity had diminished sufficiently to make the risk acceptable. The entire process demonstrated scientific and operational patience that German planning had lacked. The Germans had known about Chaff theoretically, but had treated it as a weapon too dangerous to use. The British had treated it as a tactical problem requiring careful analysis of risk versus benefit, and had deployed it at the optimal moment. The legacy of Window extended far beyond World War II. The principles of radar countermeasures, demonstrated in 1943, became fundamental to electronic warfare in all subsequent conflicts. Modern military aircraft carry chaff dispensers as standard equipment, though the materials have evolved from aluminum strips to more sophisticated radar-reflective fibers. The cat-and-mouse game between radar designers and countermeasure developers that began with Window continues today, driving advances in frequency-agile radar, synthetic aperture systems, and advanced signal processing. The fundamental lesson remains unchanged. Any detection system based on electromagnetic radiation can be deceived by appropriately designed reflectors or emitters, and the side that better understands the physics of detection will possess significant tactical advantage. For the German defenders in summer 1943, these future developments were irrelevant. They faced the immediate reality of aluminum strips raining from the sky and radar screens white with false returns and bombers penetrating defenses that should have stopped them. They lived through the transformation of their defensive network from sophisticated machine to obsolete liability in a single night. They witnessed British science dismantling German defences with elegant simplicity, while German engineers struggled to respond. The aluminum fragments on Martini's desk in Berlin represented more than a tactical surprise. They embodied the systematic defeat of German defensive technology by an enemy that had studied, analysed, and solved the radar problem, while German defenders had remained confident in their superiority. Each precisely cut strip, 27 centimetres long, half a centimetre wide, weighing almost nothing, was a testament to British scientific thoroughness and German intelligence failure. When the British called it Window, they chose the metaphor deliberately. It opened a transparent pathway through defences previously thought impenetrable. It let light into the darkness of German cities, though that light came from incendiary bombs rather than sun. It changed permanently the balance of the air war, shifting advantage to the offensive in ways that could not be reversed. For the German radar operators who watched their screens fill with impossible contacts, for the night fighter pilots vectored toward empty sky, for the flak crews firing at ghosts, for the civilians who died in fires that defences could not prevent, Window meant only one thing. The enemy had found the weakness and exploited it with devastating effectiveness. The aluminum strips that glittered in laboratory lights had written Germany's defeat in the electromagnetic spectrum long before that defeat became obvious on the ground. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.